Hello, everyone. This is Audrey Layton with Team 18. I have Maddie McGill with me, and we are going to present our project, which is the Human-Machine Interface Technology EMG Control System Demonstration Designs. This is designed for an electric power wheel. In this picture, you can see Logan Boyd. He's also part of our team. He is demonstrating the MyoAware muscle sensor controller. It was very successful as a proof of concept, and the EMG controller may be used to control an electric power wheel. Both of our team members, Logan Boyd and Najim Uddin, have presented 2 videos, and I'm going to show you them right now.
Here we go. For our project 18, we was planning to do run a wheelchair by using EMG device, but due to the pandemic and some other constraint, we are unable to proceed that far. But we have managed to make some movement on servo by using the EMG device, which is the setup is basically the sensor and electrode there, and an Arduino kit here, and that's connect to the servo. So let's try to move the servo by moving the hand. That will produce some signals. Here we go.
And so since we can move the servo with the EMG attached to my arm, then basically off that, then we are able to move a wheelchair, and we should be able to move a electric wheelchair, because the basic principle is an electric motor, which is almost the servo.
Our design involves 2 different components, which is the EMG sensor and the combined microprocessor and the microcontroller, which is called the CPU system. Once again, here's Logan demonstrating our EMG sensor design. It has a very hard, rigid metal material. The problem with this MyoAware is that it ends up being really uncomfortable over an extended period of use, and the electropads lose its adhesion whenever you're repeatedly placing it on the skin. And as you can see, it is not completely wireless. So although this product does work as far as technology goes, this just is not an ideal product for customers to wear repeatedly.
And as Audrey just said, looking at all of the problems that we saw with the commercial MyoAware sensor, by being rigid and hard and not really comfortable for someone with disability to have to wear it for extended period of time, to have that on their arm, you could see possible skin irritation and just being generally uncomfortable to wear. So what we did was start to design a first and second stage prototype of what would meet the needs of patients with upper and lower limb impairment. So as you can see on the left, we started off with just making the sensor material flexible. So the sensor material that we used was the Tegaderm. And it's Tegaderm medical tape that is used often in medical settings, hospitals, to cover wounds, surgical wounds, injuries, also to hold drain tubes and wires in place in the healthcare setting. So we knew that by it being so widely used, that it would be easy, very comfortable on the skin, to be worn, and safe, and it's been well tested. So we decided to use the Tegaderm, which has an elastic modulus of about 7 megapascals. And we put that on the skin first to simulate the sensor skin. And we decided to mount the microprocessor microcontroller on top of the sensor. As you, in the other picture, I'm not sure if it was quite shown, but the MyoAware was attached to a laptop. So with the microprocessor microprocessor, microcontroller unit as a smaller unit, it could be mounted directly on the arm as opposed to having to carry a laptop around. So that's why we chose the CPU system to be mounted on top of the sensor skin in order to make it more portable and more convenient for the user. And as you can see, it's rigid, but it's mounted. And then in testing, it performed very well because it actually stayed attached to the arm and it withstood all the torques and stresses that would occur when someone's actually using it doing operation as an EMG controller. On the right, we decided to make both the sensor and the CPU system made out of material that is flexible. So we decided to use a rubber silicone, which is basically a breast pedal, which are used when basically women use as a strapless bra. And so we know that it's safe and it's also can withstand a lot of stresses and torques. So we decided to use the silicone rubber as a material to actually use for the CPU system. And as you can see, it's mounted on top of the sensor and is more flexible. Next slide, please. This is a video of the material design that I actually made, so you could actually see how the setup works for each prototype. So on my arm is basically the tegaderm, and it's just simulating the sensor material that goes directly onto the skin. And so on the sensor skin, we're going to attach the actual CPU system directly on top of the sensor skin, as opposed to having the user to carry a computer around, so they could just literally put a portable wireless sensor CPU system on directly onto the sensor itself on the arm or wherever it's needed. And it's being attached to the sensor with body tape, and that's what I just peeled off and put on. And this is the simulated CPU system that's going to be mounted on top of the sensor. And it's being attached to the body tape and the sensor. As you can see, as far as being able to hold, it holds very well. It withstood the torques of the arm in motion, in movement, as someone be using it to control a wheelchair. So it performed well under the stresses, and we knew it would actually hold. And now I'm taking that system off and going to the second prototype that we decided to use. As you can see, this is the tegaderm is used again, and on top of the tegaderm is basically an adhesive glue that's attached to like a snap button, and that's to simulate the wire connection between the sensor and the CPU system. And as you can see, that's the breast pedal with the other end of the snap that's going to be attached directly to the sensor. And that's being snapped on. And as you can see, it's a more flexible system, and it should be more comfortable for the user to use because the silicone rubber is actually very similar to the polyurethane tegaderm that's being used. So we're assuming that since they are similar materials, then they'll perform with similar effective behavior for mechanical behavior. Next slide, please. And this is just some more pictures of the actual setup material that I use, and you can see clearer how the wire snaps that I was suggesting for use would be used in order to mount the CPU system onto the sensor skin. Next slide. So from researching flexible wearable technologies, we came up with that most often they're used doing that technology, flexible wearable electronics, they use silicone elastomers as the substrates in order to mount electrical circuits to, and it's very flexible. The elastic modulus for this particular elastomer is 0.07 megapascals. Next slide. And as you can see, the printed circuit is really printed directly on top of the silicone elastomer. And as you can see, the pattern of it is basically liquid metal that is printed, either screen printed or inkjet printed directly onto the elastomer in a serpentine pattern, which is basically a snake-like pattern in order to allow it more coverage and more flexibility. So this basically enhances its stretchability, its flexibility, its comfort. Also, it gives a better signal because more of the muscle is covered based on this kind of dense, nano-thin serpentine pattern of circuitry. Next slide. And then we see here the circuitry, the printed circuitry is basically encapsulated in a polyimide layer, and that's just to prevent leakage. So the actual circuitry will stay on the substrate and will not detach, which will cause you to have performance issues with the EMG controller. Next slide. Now for the CPU system, we decided to basically, in the same line of thinking, to try to keep the materials similar in order to make sure that they actually have the same mechanical behavior, which is what we're looking for, is more flexible, comfortable medium in order to someone to wear long term. So we decided to use a silicone elastomer substrate for the CPU system as well. As you can see, it's demonstrated here with the gray box here. Next slide, please. So we see that on just like the sensor, we're going to actually print a microchip circuitry directly onto this silicone elastomer. As you can see pictured, it's not pictured on the actual circuitry, but that's what will be printed on directly on top of the CPU system. Next slide, please. Here we're showing that how the CPU system is mounted directly on top of the sensor. As you can see, the gray is the CPU system, and the more clear is the actual sensor under the bottom. And this whole unit is going to be mounted upon the person's arm or whatever body part that is being used or needed to be used. Next slide. So here, this is just a picture of glue strip. It's sort of like the body tape that we use for the first prototype to adhere it to the sensor. But basically what we are proposing to do is design a snap wire connector between the CPU and the sensor, but also an adhesive like a glue tape or I don't know, can be used to adhere the sensor and the CPU system. Next slide. And here is a picture of what the entire two-component system looks like when it's mounted together as one single unit. And this is a demonstration of someone's arm or that it's attached to. But the idea with this whole particular design is that it is flexible, that although we're showing an arm here, it can be actually attached to any muscle that is left. So we have persons with ALS, for instance, who have serial muscle failure, and they may only have a arm, or they may only have a calf muscle. So the beauty of the EMG system controller is that they can use whatever muscle that is actually functioning to use. And so just bear in mind that we tested our prototype on the forearm, but it's actually being designed to be moved to any muscle group. Next slide.
So here we have a future sensor design. This is a very similar design to what we have, as you can see with the adhesion. The only difference is their CPU is not mounted to the arm as ours is. Here are some lists of items that we have achieved. We've demonstrated that the EMG sensor control system may be used by people with upper and lower limb impairment to operate an electric power wheelchair. We've actually been able to prove that our unit can also be placed on the leg, just as well as the arm. The arm is just easier for our demonstration. We propose a new sensor design using innovations in wearable electronics that will be more comfortable for people to wear for an extended time. This was able to be achieved due to multiple experiments. As you could tell in the MyoWear, that's after several experiments, we had ruled that out. We propose that the sensor and CPU systems can be mounted together for a more comfortable, effective, and integrated system. Doing that and having the right adhesives, we've been able to accomplish being able to keep it on the arm for a long period of time. The only improvement remaining that we did not complete, we do think that a two-component system could be fabricated into one, possibly some soldering involved into one unit. It would be more efficient, comfortable, and effective. That is all that we have for you today. We really appreciate you watching this from the beginning to the end. So if you have any questions, please let us know. Thank you so much.